Hello. In this video, we will get to know about the topic the International Data Encryption Algorithm, which is also known as IDEA. Let us know what is IDEA algorithm. It is a symmetric key block cipher encryption algorithm. Symmetric means it is reversible as a DES algorithm. Reversible in the sense in which we can enter the plain text. The plain text is encrypted into the ciphertext, and as well as the ciphertext can be decrypted into the plain text. It is vice versa. That is why it is called as symmetric. And also here we use only a one key for both encryption and as well as for the decryption purpose. It is designed to encrypt the text to an unreadable format for transmission through the internet. That is, it is designed to encrypt the text. The plain text is converted into the ciphertext, that is, which is unreadable format. And it is done with the help of internet. So the plain text is converted to the unreadable format of the ciphertext. This is also known as IPES. This is used as a replacement for data encryption standard. That is, it is also used for the replacement of the DES algorithm. It uses both the substitution and as well as the transposition in the algorithm. We use the techniques of substitution, and as well as the transposition in the algorithm. Coming to the key blocks and transformation rounds. In this algorithm, we will be having keys, blocks, and as well as the transformation rounds. Usually, we will give 64 bits as the input, or else 64-bit data if it is given as the input for this algorithm. And in each and every round, the block gets divided into 4 portions. That is, 64-bit data is divided into 4 blocks, which is of 16 bits each of size. And it uses typical key of 128 bits. The original key, which is of 128 bits, it is the key size from which 52 subkeys will be generated. So the original key is divided into 52 subkeys, which is each of 16-bit size. IDEA performs 8 identical transformation rounds and the encryption and decryption rounds using 6 different subkeys, which is of 16 bits each. So in this algorithm, we will be having 8 rounds, and in which the encryption and as well as the decryption is performed with the help of the subkeys, which is generated from the 128-bit original key, and 1/2 round which uses 4 subkeys, which is of 16-bit. So the one round is generated with the help of 4 subkeys, which is of 16-bit each size. And the output of this algorithm will give a 64-bit text. So the input is 64-bit and as well as the output is also the 64-bit ciphertext. This is only a theoretical part of this IDEA. We will get detail into all this key generation and the rounds technique further in this video. Let us come to the diagrammatic representation of this. Let us come into the diagrammatic representation of this topic. So basically, we take input 64 bits. We take 64-bit as an input. This is divided into 4 portions of P1, P2, P3, and P4. Let us look at into this this thing. That is 64-bit input, that is plain text, is divided into P1, P2, P4, and this is of 16 bits. This is of 16 bits. This size of P1, P2, P4 is 16 bits. Similarly, so for this P1, P2, P4, we will perform the round operation, that is R1. We will be having 8 similar rounds, which is of like P5, P6, P7, P8 for the second round. In the same way, we will be having 8 such rounds. And we uses key for each and every round. So for this round function, we also use the key. We also use the key. This key is generated, this is the sub key, which is generated from 128 bits. And we use 6 such keys, that is K1 to K6. We use 6 such keys for each and every round. So the last round, that is the output transformation, that is it produces the ciphertext with which uses the 4 subkeys. Here we have discussed, we will be using K1 to K6 for each and every round. So there will be 6 keys for each, 6 subkeys for each and every round. But here we are discussing that 4 subkeys is only needed for the 8th round. So we will be left over with 2 subkeys. Let us discuss what those 2 subkeys will be doing further. This is the diagrammatic representation. This is the diagrammatic representation. As we have discussed that we'll be having 64 bits. Each is divided into 4 P1, P2, P4. Here we'll be having the key, that is K1 to K6, K7 to K12. In the same way, we'll be having up to 52. So one round will be having the 6 keys, and 8 rounds will be having 8 into 6, that is 48 sub keys. Now let's discuss, we'll be having some operations in this algorithm, that is the round function, and as well as the key generation thing, and as well as the output transformation. We will get into know in detail of these 3 subtopics in this video. The first thing is single round details, that is the round function. This is a simple mathematical operation needed to be performed in order to get this round function. That is, we will be having the input, that is of plain text of 64 bits, which is divided into 4 portions, that is P1 to P4, which is of 16 bit each size, that is P1, P2, P4, P3, P4 respectively. And then the original key, which is of 128 bits, it is divided into 16 bits key, like K1 to K6. And in this round function, we will be having 14 steps. And in step 1 and step 4, P1 and P2 are multiplied with the sub key K1 and K4 respectively. In the step 4 and in the step 2 and 3, we will be having P2 and P3, that is added with the K2 and K3 respectively. In the step 5 and step 6, we need to apply the XOR operation in between the results which we got from the step 1 and as well as the step 3 and the result of step 2 and as well as the step 4. That is why initially we have done the operation with step 4 and step 6 and as well as the step 2 and step 3. In step 7 and step 9, the results of step 5 and step 8 are multiplied with the K5 and K6 keys respectively. So in the step 8 and step 9, we need to add the results of in the step 8, we need to add the results of step 6 and step 7. In the step 10, we need to add the results of step 9 and step 1 and step 9. In order to get P1, P2 and P4 respectively, if the multiplication value, when we are doing multiplication, when we get the value which is greater, then we need to apply the mod operation. That is why our output will be simplified. While sending the new P1, P2, P4, P3 and P4, the order is shifted to P1, P3, P2 and P4, but that is not seen in the round data. So P1, P2, P3 and P4 is sent in the same order to the output transformation from the round data. Next thing is 52 subkey generation. As we have discussed earlier, the original key is of 128 bits and the original key is divided into 16-bit subkey and each to obtain 6 such keys for each and every round. Totally, we will be having 19 bits that are utilized in the round 1 to generate the subkeys. So in this 128 bits, only these 96 bits are used and we are left over with the 32 bits. These 32 bits are unused bits. So these bits are used in the next round along with the newly generated keys. So for to generate this round function, as we have discussed here, we require only 4. We require only 4 subkeys. We will be left over with the 2 subkeys. So that is why for the round 2, we will be using the same 2 keys and we will be generating 2 more such keys to get the 4 subkeys for the second round. So here we can see that initially the size of the key is 128 bits. This is divided into K1 to K6, that is 6 subkeys. So we'll be left over with these unused bits, that is 32 leftover bits or unused bits for the so these new that unused bits. So these 6 keys will be used for the first round and these unused remaining bits will be sent for the next round. That is, we will be having K1 and K2 for the round 2. So here, in order to generate this 128 another bit 128 bit key, that is it should be unique for every round, right? The key should be unique for every round. So in order to generate this unique 128 bit key, we will be doing an operation called circular left shift by 25 bits. That is, if we have the key as 0 1 1 0 in the binary form of 128 bits, initial 25 bits is taken from the front and it is added back of it, like these 25 bits is removed from this binary thing and it will be added backside of it, like it acts as a circular left shift up. These left bits will be removed and then it is added to the right of the bits. That is why we will be having no difference in the size of the key. That is, it remains 128 bits same time for every round, but we will be generating the unique new keys. That is what they discussed here. This new 128 bit key is used to get other subkeys by dividing the new subkeys into 16 bit keys. This method is followed by rest of the rounds. So in the same way the round 1 operation is performed. All other 7 rounds will be using the same round operation in order to generate this algorithm. So each of the 8 rounds make use of 6 subkeys. That is 8 into 6, 8 rounds will be, and there will be 6 subkeys. That is 48 subkeys that are required for the rounds. The final output transformation uses the 4 subkeys. So since all rounds uses 4 subkeys, the final round, that is round 8, will also use the 4 subkeys. That is 48 plus 4 is equals to 52 subkeys overall. So finally also we will be having 4 more subkeys. So that is why the count is equal. That is, it will be having 52 subkeys overall. From an input key of 128 bits, these 252 subkeys are generated. So finally the count is matched. That is, initially it is 128 and final key also is of 128 bits. That is 52 into 16 into 128 bits, and finally they are matched. And the next thing is output transformation procedure. So this is one of the half round. So this is one of the half round of this output, and the input of this round bit is 64-bit block. So 64-bit block is divided into 4 blocks as we have discussed earlier. This involves the usage of 4 subkeys. This results in round 8, that is R1, R2, R3 and round R4. So we need to remember these 4 particular steps in order to get this output transformation procedure, which comes after the round 8. In the step 1 and step 4, we need to multiply the R1 and K1 with the key K49 and K52 respectively in order to produce the C1 and C4. C1 and C4 are the ciphertext. That is, since we have generated initially P1, P2, P3, and P4, the output will be in the form of C1, C2, C3, and C4. That is the ciphertext. In the step 2 and step 3, the R round 2 and R3, round 2 and round 3 is added with the K50 and K51 keys respectively in order to produce the C2 and C3. So we need to multiply the K1, R1 with K1. We need to add R2 and K2 and add R2 and K3. And in the step 4, we need to multiply the R4 and K4 in order to get C1, C2, C3 and C4 respectively. And these are combined together to get the 64. So each and every block, that is C1, C2, they are of 16-bit size. So that is why they are combined together into 64-bit ciphertext. 64-bit ciphertext. So that is why our initial condition and final condition are satisfied. That is 64-bit plain text is converted into the 64-bit ciphertext with the help of these round functions, and as well as the key generations. With the help of keys in each and every round, we will be encrypting the plain text into the ciphertext. So this is IDEA algorithm. This is also known as symmetric key, which in the same way we can also do it vice versa. That is, we can also do the decryption algorithm also in the same way, that it is reversible manner. So that is why the output ciphertext can also be converted into the input plain text by going through these functions, that is round functions R8, R7 to R1 in order to get the plain text. That is why both the plain text and as well as the ciphertext will get matched and our output is satisfied. Both encryption and decryption is done along with the key generation. This is all about IDEA algorithm. Thank you.